Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our special session on citizen science, specifically citizen astronomy, and how everybody can participate to the research we do in astronomy. For this panel discussion, I invited three panelists who's going to discuss their contributions to citizen astronomy. So first we have Mark Kushner. Hi, Mark. How are you?
Hi, Frank. Thanks for having me.
So Mark is a citizen science officer at NASA, and he's going to tell us about his program related to the search for Planet 9. And then we have Rachel Knight. Hi, Rachel.
Hey, everyone.
So Rachel is a citizen astronomer who has been involved with UNISTELLAR on the defense of our planets against asteroid impact. And then we have Connie Walker. Hi, Connie.
Hi, thanks for letting me be here.
So Connie is an astronomer at the NOIR lab, and she's going to tell us how we can help preserving the dark skies. So let's start with you, Mark. But before talking about the NASA program, let me just play a video which kind of summarize one of the program you will mention. Okay, so Mark, tell us about this program, the Backyard Worlds Planet 9. What exactly you are looking for? What are you expecting from this program?
Thanks, Frank. Maybe I should introduce myself. So I'm Mark Kushner, and I'm an astrophysicist, and I'm also NASA's Citizen Science Officer. And I started Backyard Worlds Planet 9 back in 2016 with Jackie Faraday, my colleague. And I was really inspired by my former thesis advisor from back when I was in graduate school. He's a fellow named Michael Brown, and he and Konstantin Bagadin had noticed this pattern in the distribution of Kuiper Belt objects, which are these icy bodies in the outer solar system. And they started wondering if there was another planet out there that we have never seen yet that's pulling them around with its gravity. And they called it Planet 9, and there was a lot of fuss about it. And of course, you know, I want to show him how awesome his former student is and find his planet for him. So I thought I'll go looking for it. Of course, the sky is really big and we don't know where this thing is. So it occurred to me I'd probably need some help. So I started a citizen science project to go search for Planet 9.
Okay. So this, how do you create a citizen science project like that? What do you ask people to do exactly?
We ask people, first of all, to go to backyardworlds.org. And it's a site which is powered by Zooniverse, which is a large community of citizen science projects. And you go there and you look at a short tutorial, and then right away you'll be looking at data from NASA's WISE mission, which made the latest, greatest images of the whole sky in the infrared. And very quickly you'll be looking at data which maybe nobody else has seen before. And we display it in a way which lets you blink between images taken in different years. So Clyde Tombaugh, when he discovered Pluto, had set up something quite similar. He used this device called a blink comparator, and he looked at images of the sky in visible wavelengths, one from one year, one from another year, and he looked for things that moved, because the stars, they move, but they do it really slowly. And stuff that's in the solar system is orbiting the sun, so it flies, okay? And also objects that are near the sun go relatively fast. So we have set it up so that you go to the website, and you'll be looking at a blink not of 2 different years, but 4 different images. And you'll be looking for dots that are moving in a line. There'll be a lot of moving things on those images, but the things that you're looking for are marching along in a line like they've got somewhere to be. And if you spot one of those, you flag it, and there are multiple different ways you can report it to us. And we'll put it on our follow-up list, and maybe you found a planet, or maybe you found a brown dwarf. And brown dwarf science has been buzzing in this project, and I'll tell you some more about that if you're interested.
Yes. So how many people are we talking about here? You mentioned this program is hosted by Zooniverse, so talking about 1,000, 100 people, so even more.
it's hard to say precisely, but about 175,000 people have participated in the project so far. Of course, they participated at all different levels. Some of them stop by. They're, are casual users. They stop by and they try it out and they do a little blinking and it's fun and then they leave. And that's great because if you put together a lot of contributions like that, you can make a big dent in a scientific problem like this. Also, we have people who stick with it for years and who have become my co-authors on scientific papers. So we've had, I was just counting them up, 25 of our citizen scientists are now co-authors on scientific publications as a result of their work on Backyard World's Planet 9. We are so proud of that.
So those are people who basically are really involved in the project, follow up, you have a conversation with them as well.
They're an extension of the science team. We have regular weekly video meetings with them, and they're all around the world, and they're brilliant and they're hardworking, and they inspire everybody. It's one of the deep rewards of doing citizen science.
So what kind of findings? I don't think they found Planet 9 because I would have heard about it, right? But I'm assuming you have found some more things.
You would have been my first phone call, Frank. I would have called you up and be like, we got Planet 9. Yeah, so we don't have that one yet. Stay tuned. It may be hiding in the galactic plane, or maybe it's at aphelion, right? Maybe it spends most of its time in its orbit at a great distance from the sun. So, out there it's cold and dark, so it's hard to spot it. But we have, in the meantime, busted apart the field of brown dwarfs. We've got 3,000 total brown dwarfs that our volunteers have discovered. So you can see a new map put together of the brown dwarfs near the sun out to about 65 light years. And it's about 500 brown dwarfs, and we've discovered 52 of them. People have been looking for these things for decades, right? And we just came in the last couple of years, and we've already discovered 10% of the nearest ones. So a brown dwarf is a ball of gas, like Jupiter. Jupiter is a ball of gas, but we call it a planet because it orbits the sun. So if there's a ball of gas out there and it's not massive enough to be sustaining a fusion reaction in its center, then we call it a brown dwarf. But some of them, you may as well call them planets, sort of planets without stars. Others are more like stars, but there's a whole range of interesting things. And, one of the goals of brown dwarf science is understanding where star formation ends and where planet formation begins, mapping the nearest objects, because the nearest objects to the Earth, most of them are brown dwarfs, not stars. Sorry, beyond the solar system, nearest objects to the sun. The best discoveries are the volunteers themselves. You know this well, right? From your own project. The people just make your day.
How are most people finding out about your program, and are they high school students, college students?
We have everybody. We have retirees, we have high school students, we have moms, we have kids, we have other scientists, we have lawyers, we have musicians. Everybody loves astronomy, right? And so we figured out a way to make it simple for people to do cutting edge astronomy. We had a lot of help, from Zooniverse and so on. But so we get to meet lots of people who share this passion with us.
All right, thank you very much, Mark. So we will post the link for people who want to join your program and become citizen scientists and discover brown dwarf, missed stars, or almost planet. I don't know how you want to call them. Rachel, since you were just talking a bit, let's maybe play first a video. Since I would like you to discuss your experience as a citizen astronomer for the UNISTELLAR Planetary Defense Project. So Rachel, I introduce you as a citizen astronomer. But in fact, you're more than that. You are not only a citizen astronomer, you're also working in the biotech industry as a finance. You have contributed to a lot of our programs at the for the UNISTELLAR network for the study of near-Earth asteroids. Can you tell us how you went through this and what kind of discovery you have been involved?
So hello, everyone. My name is Rachel Knight, and by far, I'm the newest person to this panel and newest person to astronomy, frankly. I didn't even own a telescope prior to about a year and a half ago. I have a degree, kind of like Frank mentioned, in an unrelated science, and I work in a field unrelated to astronomy. My husband was an early backer to UNISTELLAR's Kickstarter, and we got the telescope a few months before things really started locking down last year. I dabbled in the beginning, looking at kind of galaxies and nebulas, star clusters. But after working from home full time, I really got into backyard astronomy. It became kind of my hobby. I know a lot of people did sourdough bread baking, but I was getting up at all hours of the night to really start looking at the stars.
So what is your contribution? What made you become a citizen astronomer beyond the pandemic?
Yeah, I think what really started sparking my interest was the ability to contribute to citizen science. So every month, the Unistellar network would send out targets to point the telescope to. It's often a matter of just going on the app to click on the asteroid, and the telescope kind of does its thing and points to the target. But I've also gotten okay at calculating where to point the target to using NASA's Jet Propulsion Laboratory website. So the missions come in a few flavors, and there's occultations where you kind of watch an asteroid pass in front of a known star and you get enough people to look at it and you start mapping out the shape. And I haven't been able to catch one of those yet, but some other people on the Slack channel and the Facebook group, Unistellar has a big network where we all kind of chat online. They've managed to catch some, so it's always kind of exciting to see what they've done. I think though, where my big success though has been is in what you guys call kind of planetary defense missions, or I'm going to call endurance missions because they're often kind of all night long recording sessions. So there's one specific target you look at for an entire month, and you kind of point the camera at the telescope to, and it takes a lot of images over time, kind of like an HDR camera will take a lot of shots and kind of layer them on for better range. That's kind of what the telescope's doing.
What exactly do you see? You watch the asteroid, and what kind of measurement did you get?
Looking at kind of the asteroid, so the first asteroid I really looked at was called 787 Moskva. And I looked at it kind of in August of 2020, and I believe they're going to put on the screen an image of it kind of tracking against the sky. So that image was a recording of about 3.5 hours, different screenshots about every 30 minutes. And so you can kind of track the path of the asteroid as it moves across the sky. And what the telescope is really looking for is kind of the changes in the light dynamics, and that helps make a light curve. So if we think about asteroids, from what I understand, they mostly look like little almonds, and kind of as they rotate around themselves, the light reflecting off of them changes. And so you can kind of compare it to the stars around it and make a light curve, which kind of looks like a sine wave graph. But once you get enough of that data and kind of combine it, you can really start mapping out the 3D shape of an asteroid, which is frankly really cool. I think with 787 Moskva, my partner and I actually did shifts because we tried to capture it in a 6-hour recording. So I'd take the early shift, I'd wake him up at like 1 a.m. He would come down and he would manage the telescope for the rest of the night until say 4 a.m. when we got enough data.
You basically partner with a partner, and you observe continuously Moskva for an entire night. I'm impressed. I didn't know this story. So this is an asteroid, basically. That's a mock-up of an asteroid. So they're not spherical, as you mentioned. They have this always kind of almond shape, especially the smallest one. And by doing light curve that you mentioned, you can get a 3D shape. Were you involved as well in 1999 AP10?
Yes, so that was my second mission, and I think we did 8 different recordings, the longest one being 6 hours, but most of them over 4 hours. And I think 26 other citizen astronomers kind of helped get many different observations of that one in 7 different countries. So we had lots of views from across many different places over the course of, I think, 2 months. And that really started mapping out. I think that asteroid video you showed in the beginning, that's kind of what we came up with.
Yeah, that's the shape of 1999 AP10 by what we call light curve inversion. Where do you live, by the way? You live in the city or in the countryside?
I'm in the suburb of California, kind of near Los Angeles.
I was wondering what surprised you about doing this kind of science? What was something that you learned that surprised you?
You know, it's surprising to me how much is still available to backyard astronomy. You would think kind of anything we can see with a cheap enough telescope that I can afford it would have been discovered by now. But there's so many things moving and out there that not everything can point to everything. Not all weather cooperates at the same time. So it's very cool to be able to be, frankly, in my backyard and contributing to science.
There's going to be a very exciting telescope, new technology telescope coming online in the next few years called Rubin Observatory. And they're going to be doing a lot of asteroid searches as well. Do you think there'd be some chance for a collaboration where the backyard astronomers could either share what they've detected for further observation or vice versa? Perhaps they could ask you to follow up on things. I think that would be rather exciting as well.
I mean, I think there's always an opportunity for kind of more data points, right? That's the kind of the next wave of the future. The more data we can collect, the more people can analyze it, the more, frankly, we can do with it. And so more telescopes, more people looking. Let's make big databases so we can all start looking at that data together.
Well, thank you very much, Rachel. That's exciting to see that with a small telescope in the backyard, you can basically help defending the planet. We should mention that the size and the shape of an asteroid is really key to understand how the asteroid trajectory will move due to interaction with the solar wind or the Yarkovsky effect. We call that an acceleration introduced by the heat coming from the sun. And that's one of the reasons it's very important to characterize very well those asteroids, to know the shape and the size way in advance. Connie, you are going to talk a lot about fighting light pollution, and we do have a video again.
Night after night, the stars shine down on us as we looked up at them until the invention of electricity. In 1882, the Pearl Street Generating Station came online in New York City and powered 400 of Edison's fabulous new invention, the incandescent light bulb. Within 2 years, there were 10,000 light bulbs now being illuminated. And that number has continued to grow ever since, even to this day, 137 years later. Today, this is what our Earth looks like at night from space. It is as if the stars themselves fell out of the heavens and landed on Earth. There is so much light coming off of the Earth now that 80% of North Americans and Europeans can no longer see the Milky Way.
I was just going to say, Michael Marlin is one of our dark sky ambassadors for the International Astronomical Union, and he did that video. Well, it's part of a bigger video for this Globe at Night campaign, which is really, really wonderful.
Thank you. So Connie, you the head of the Globe at Night program. So can you tell us why the dark skies are important for us to preserve?
Well, there are two basic reasons. One that's a little bit selfish, because astronomers want to have a dark sky to receive faint signals from light from distant galaxies in outer space. And that light, the night sky itself, gets washed out by very bright stars from streetlights from cities. And that's what's known as light pollution. So the reason that astronomers want to study objects like distant galaxies is because they hold the clues to the origin of our universe. And as astronomers look further and further away to more distant galaxies, they're looking back in time, actually. That's why we say it's to the origins of our universe. Dark skies are very critical then in terms of scientific resource for understanding the origins and the mysteries of the universe. The second reason is, I think, even more important in some ways, because dark skies are a very common and universal heritage that we all share. It is a very important part of the cultural and natural heritage of all civilizations. And people were much more connected to the rhythms and to the wonders of the night sky before the widespread use of electric lighting. And the sky marked the changing of the seasons, the passage of time. It represented order, yet the sky, is mutable. And then so throughout history, the night sky has shaped our beliefs and our traditions in various societies, from, say, the myths of the ancient Greeks to the celestial aligned buildings of several ancestral Native American nations, to agricultural harvest festivals and nautical navigation records that we have of sea voyages to new and distant lands.
Okay, so the motivation to create the Globe at Night, maybe you should explain what kind of citizens project it is and how people can participate to this challenge of protecting the dark sky.
Well, what I really enjoyed hearing here with the other two projects is how homegrown some of these things are initially, and how citizen scientists play such a vital role, because not any one of us in the projects can take all of the data all of the time in various parts of the world. So it's hugely necessary to have citizen science involved. And for us, it was a very homegrown project because it started actually at our two cities that are nearest our observatories, namely in Tucson and in La Serena, Chile. And those two communities have in common Hispanic students that we actually had video conferences with back and forth, and decided that this was a very important project that we could do that was in common to both locations. And the kids really got into it. So we only had a map with colored pushpins denoting what kind of bright or dark sky they had. And this caught the attention of Globe. It's a organization in Colorado that took the project and made it online within months, and it became widely used internationally ever since. And that was 15 years ago now. And so the primary thing we wanted to do is to actually change the mindset of a society that's used to turning night into day, basically. So it was built on mostly awareness more than anything else. To try to get the public involved, and especially the next generation, in understanding what the issues are surrounding light pollution and the solutions. And so basically Globe at Night is an international citizen science campaign to raise the public awareness of that impact. And so we ask citizen scientists to record the night sky brightness by matching their view of what they see with a constellation like Orion, which is up right now. And you have 7 different maps, and you're not counting stars. I underscore, you're not counting stars. You're asked to just look for the faintest star you can see toward Orion and match it with the faintest star you might see in one of 7 maps. And I can explain that later if you'd like. So it's going on for about 14 years, as I said, with 180 countries involved and more than 2/3 people. And last year, I know it's not a big number for a lot of different projects that Zooniverse has, but we had 30,000 Globe at Night measurements, which is a record high for us from over 100 countries.
That's impressive. But I think it's interesting how people are realizing more and more that we need to protect the dark sky. People have a hard time understanding how bad it is. Maybe you can explain that about this kind of an analogy with the Milky Way.
Well, you were noticing in the introductory video for Globe at Night that maybe 140 years ago or so, the Milky Way could be seen almost anywhere in the world. And then there was the advent of the electric streetlight. And so now, just a few years ago, they counted about 300 million electric streetlights around the world. And so that, the statistic that about 80% of the people in the United States and in Europe say they have never seen that beautiful arch of the Milky Way across the night sky because they live in these light polluted cities. To gain a sort of a measure of how bad it is, there's about 70% of the electricity that is used to generate these lights are done by burning fossil fuels. And that's, again, another source of pollution, air pollution, and also accumulation of greenhouse gases. And there's a ton of other things, like the amount of energy wasted is billions of dollars a year because you're not shielding lights. You're letting the lights shine up where it's not needed. You have lights that stay on all night, and that's not needed. So it's a waste of energy again. You have glare for the aging eye, which creates all sorts of hazards, or light trespass into the bedroom, which makes it difficult for people to sleep, or blue light that causes certain bad things to happen in terms of human health and disruption of your circadian rhythm, because we're day and night animals. So all sorts of things like obesity and depression and sleep disorders and diabetes can be linked to all this. And also the biggest thing about the blue light is the cause of the melatonin levels at night to be depleted. And that's been tied to a couple different kinds of cancers. And the biggest thing for me, though, is also how it disrupts the habits and habitats of animals. That's really crucial because their survival sometimes depends on dark night sky for migrating birds and hatching sea turtles. So it's a lot of different things in addition to how it affects astronomy.
All right. So we saw the previous project, you need a computer to do comparison or buy a telescope in the case of Rachel. So what about you? What do they need to do, those citizen scientists who want to
Oh,
participate to the Globe at Night?
well, no special equipment's needed whatsoever, just your eyes and hopefully a cell phone or a computer, basically. So Globe at Night is formulated so that 10 days during each month, there's no moon. Well, we can't predict where the moon's going to be, but based on where the lunar cycle is, we can say the first half of the evening during 10 days between third quarter moon and new moon, you can take data in the first half of the night. And you just have to know of certain things like, well, you want to go out an hour after sunset, you want to have your eyes adjusted to the dark, and you want to turn on the little tool we have to make your cell phone, which has the Globe at Night report page on it, in sort of night mode. So it's not a light source for you. So no moon, an hour after sunset, and get your eyes dark adapted. That's about the only things you really need. And then, of course, if you have our report page in front of you, you can do 5 easy steps and you're done. And if you have a smartphone, for instance, the first 2 steps are done for you, because what it asks you is basically only the date, the time, and then the second step is your location. And that can be put in by a smartphone automatically. And then the third step is where you choose your chart. And you'll have 7 charts. The first one is like New York City, where you only have a couple stars. And the 7th chart is like the national park, where you cannot tell one constellation from another, right? So you have many stars. So those are different levels of light pollution, from lots of light pollution in New York City, chart number 1, to very little, or if any, light pollution in chart 7. And then after you've chosen which chart it looks like what you see in the night sky, then you leave it there. The chart, you're clicking on things, so you leave it where you clicked it as a match. And then you go to the next question, which is only the weather. And you have 4 choices: clear to progressively more cloudy. And we hope you don't take it when it's cloudy. Thank you. Data can't really be used. And then you just have a part where you can actually enter. You don't have to, but you can actually enter what they call sky quality meter data with this little thing that's no bigger than a matchbox. A lot of people have this that are actually amateur astronomers and in schools and stuff. We've given hundreds of these things away in our education kits, and you just hold it above your head. You point the sensor up, the sensor here up, and you hit the start button and read off the number and put it in the report page, and you're basically done. You just submit the data. So within a half a minute, or no more than a minute, you're done with your measurement for at least one Globe at Night data point. But the biggest time sink is waiting for your eyes to become dark adapted, they say. And that's about it.
Yeah, so I heard that you involved some high school students in this project. Maybe.
Oh my goodness, we had so many incredible results, and one of them, as you say, was with a high school in Norman, Oklahoma. Actually, there were 2 high schools, and a bunch of students led by a woman named Eileen Grabowski, and her affiliation with a number of amateur astronomers in the region. And they collected a grid map. It's a grid map that was taken of Globe at Night data, both visually and with the sky quality meter. And that data, you could see the bright areas that were attributed to globe lights in the university area. And those were lights that shine everywhere but where they're supposed to, namely downward. And then there were lights similar to those that were in the business area of the city. And they were able to take that, that evidence basically, and go to their city council. And it took 2 years actually to get the laws strengthened, but they did it. They actually made stricter lighting ordinances. And that's one of our really great examples of what can be done with the Globe at Night data.
That's great. So a project has been already providing some kind of data that's useful to change the policy in a city, or to give better sky to the people.
I was wondering, Connie, what would you say to Elon Musk? He sometimes comes to South by Southwest.
Well, I'm involved with the satellite constellation kind of light pollution that's happening. I'm very involved with that. And we've been talking with SpaceX quite a bit for about 1.5 years now. So, and there are a number of things that have gotten done because of the dedication SpaceX has to mitigating that problem, which is they put up DarkSat, they put up VisorSat, and now they have something else online, I think, that they're thinking of to try to make it less light pollution for people visually, and also for astronomers taking data, so that we're trying to get it so that the images are not saturated, which at this point they still would be. So, so yeah, I'd say, let's keep working together is what I'd say.
Is there a reason to take more than one data point in a particular location?
Yeah, because it's a statistical thing, right? You want to have, when I work with students, I usually ask them to take at least 3, if not 5 in one location, and then move around maybe a half a mile in all directions. We have a program called Adopt a Street, in which they do just that. So families will adopt a street and take every, half a kilometer or a mile, say, data, and submit it to Globe at Night, so we have a good map of the city. So those kinds of strategies have worked out really, really well.
Well, thank you very much, Connie, for taking care of the dark sky for us. It's great.
Well, thank you for inviting me.
Of course, appreciate the effort made by you or the groups to preserve the dark skies and allow all of us to enjoy the Milky Way and observe faint objects with their telescopes.
Well, it takes everybody to do this. That's the key.
The sky is for everybody, so that's the reason. We all need to be involved to preserve it. Okay, so I'm gonna be the last one to talk about one of my projects that I've been developing with the UNISTELLAR network, which is to search for new planets using small telescopes. And I also have a video.
The EV Scope is also a portal to an active community of people who share knowledge and enthusiasm, tips and challenges. A thriving ecosystem where each user can even join forces with scientists to make major discoveries.
So these videos show basically one of the programs we have been developing with the UNISTELLAR network, which is the search and the characterization of exoplanets. So first, I should really mention what exoplanets are. So exoplanets are planets in orbit around other stars. It's remarkable that the first one that was published and advertised was discovered in 1995 only, so a few decades ago. And now, thanks to NASA instruments like Kepler and now the TESS, we know more than 4,000 of them. We don't see exoplanets directly. It's very rare. We have very few pictures showing a planet in orbit around other stars, because planets are very small in comparison and very faint in comparison to the star. So what we detect, it's an indirect way. We don't see the planet, we see the shadow of the planet as the planet is orbiting between us and the host star. So if you look at the star for a long period of time, if there is a planet in orbit around it and you are by chance exactly in the right line of sight, you will see a tiny attenuation of the light, which we're talking about less than 1% in the case of a Jupiter-sized planet in orbit around a G-type star, a star like ours. So this is a technique used by the Kepler mission for 4 years, and now by the TESS mission, which has been launched almost 2 years ago now, to search for exoplanets in orbit around other stars. So what we found out is that in fact there is exoplanets almost everywhere. There is around 200 billion stars in our galaxy, and we know that there is in average 2 planets per star. So we're talking about a lot of exoplanets in existence in orbit around stars. So those missions are great because they detect the small attenuation, but most of the time they cannot go back to the same target to confirm it. What we've been doing is to ask people, part of the UNISTELLAR network, to help NASA and TESS to confirm the existence of those exoplanets. So we have a program in collaboration with our partner, our scientists that we work with the TESS mission, and we receive some alerts when a target of interest, a TOI, has been discovered by TESS, and this TOI is observable by using the UNISTELLAR network. We then launch the alert to our network, And Rachel, you may have received some of them, I'm assuming. And we asked those users to observe this potential planet from the backyard and send us the data that we process. And then we will confirm or not the existence of this exoplanet. So we started this program several months ago, and we already have some interesting results. So one of them is it's a light curve that we collected of a planet which was known. Sorry, it doesn't have a nice name. It's called HD 189733b. It's a planet size of Jupiter in orbit around a G-type star. Again, it's very close to the star. It's orbiting in a few days, and this one is 2 days roughly, to give you an idea. So what we did with this program, and I'm going to show the light curve here, we asked our user to observe this transiting exoplanet at the same time. And by combining all the observation from the UNISTELLAR telescopes, we had 3 observers at the time, we basically get a very good light curve. When I say good light curve, it's basically the flux of the star dropping due to the presence of the planet. And from this light curve, we can derive the timing of the transit, so the orbit of the planet. And if we repeat that multiple times at different transit while the planet is orbiting around the star, you get, of course, a better orbit, more accurate. So you're capable of predicting when this transit will happen in 5-10 years. So people often ask, why do we care to know when the transit will happen in 5 or 10 years? Well, it's because we are launching now mission or envisioning missions that will be able in the future to characterize those exoplanets. So being able to predict accurately when the transit will happen in 5 or 10 years, or follow up this transiting exoplanet for a long period of time, will save a lot of telescope time. Imagine you have telescope time to observe the same planet that I mentioned, HD 189733b, with the JWST in 5 years. Well, you need to know exactly when this transit is going to happen, because you don't want to spend the time, so the money of JWST, to operate JWST, to observe nothing. You want to have the observation of the transit exactly almost when it happened. So you get information, for instance, about the color of the atmosphere, the composition of the atmosphere. And that's the kind of work we've been doing with this program. There is more application. One of them that I just to mention very quickly is that by measuring the timing at different period of time, we may see some small variation of this timing. And this small variation could be due to the presence of other planets in the planetary system. That's the way the Neptune has been discovered, for instance, but what we call this gravitational tugging, the motion of the planet due to the presence of another one. And this can be also done for exoplanets. We can discover other exoplanets, like super Earth exoplanet, just by looking at the effect of those super Earths on the Jupiter-sized exoplanet. So this program is a way for astronomers, amateur astronomers, citizen astronomers, to participate to the discovery of exoplanets, to be involved in one of these new range of science that we're doing now with the discovery of those thousands of exoplanets in our galaxy.
I was wondering if you've been working with some different colleges and universities, groups of people, working together with a single unistellar scope.
That's a very good question. In fact, we are working on that at the moment. One of my students, Dan Peluso, is working on putting together a network of schools, community colleges, in collaboration with SETI Institute, to work on specific programs like the follow-up of exoplanets. The reason we're doing this, because this telescope it's relatively low cost compared to those telescope you can buy, the 1 meter telescope, for instance, but you can do still good science with it, like this detecting exoplanets. And having school working together across the US, for instance, is amazing, because we can observe an exoplanet transit for a long period of time during since we will have bases telescopes separated by thousands of kilometers, so a different time zone. So they will be able to continuously observe the transit. And in some cases, we have planets for which the transit have been seen one or twice. We call them long period exoplanets. And we don't have a very accurate estimate of the timing. It's plus or minus 5 hours sometimes. So having a network working across the nation will basically allow us to detect those exoplanets as well.
There are across the United States and mostly the United States and parts of the world too, there are things called teen astronomy cafes. And we've had some in Tucson done on exoplanets. And I don't know if you would like to talk further later about maybe, sharing this, what you're going to be doing in the future, especially with tests with these kinds of groups across the United States. It might be exciting.
Yeah, definitely. The goal is really to bring astronomy to everybody, schools, community colleges, as I mentioned, university, but also hopefully one day some people will be able to get these telescopes and participate sporadically to some of the programs we mentioned. Could be in planetary defense, could be exoplanet transit. And discussing this program and getting more people involved in this program will enhance the baseline of the number of bases. So hopefully also increase significantly the number of scientific results we can get.
I really like how citizen science is not just about the data collection, right? We talked about that, but it's also about the data analytics part. And that seems like it's becoming more and more for citizens as well.
Yeah, Mark mentioned that to one of a citizen science conference, that citizen science is not only about collecting data. Everybody, basically, if you're an observer, a theorist, a data computer scientist, you will find something in citizen science astronomy that you will be able to contribute and like. Universe is broad and vast, and there will be always something that you will like to be more involved. It could be looking for brown dwarf for planet 9. It could be finding, characterizing asteroids that could impact Earth, or it could be as well analyzing, contributing to preserving the dark sky by doing measurement with your cell phone. And I think it's important to involve people in our science, because they do realize that it's something that will help them as well. And it's also something that is accessible. Science is for everybody. It's not only for academics and scientists in the lab. Science is the way of thinking as well. And the scientific method should be brought to everybody. And I think with those projects we are doing this. We are bringing a science in every home.
Oh, I want to sort of follow up on that and maybe throw out a challenge. So Rachel mentioned that we have citizen scientists who are making observations, they're collecting data, and they're citizen scientists who are analyzing data. I think that there could also be some citizen science projects that are about making the theories, making astronomical theory. So, for example, there are projects like Fold It, which have been doing essentially theoretical biology, protein folding. And I've yet to see the equivalent project in astrophysics. So if you're watching and you're an astrophysicist, I hope you'll take some time to think, how could you harness the passion and the brain power of a few thousand helpers to come up with your next interesting model or interesting hypothesis?
That's a very good point, Mark. And I think that's a very good way of finishing this discussion. So thank you very much to all of you for your time and for participating to this panel discussion on citizen science. And I will just remind our viewers here that they can watch this video and post comments. We will take the time to answer to them as the South by Southwest week is happening, but also before and after. So this is a conversation that we would like to continue with you. And please visit the website that we mentioned, participate to this great scientific project if you have an interest. And thank you again, Rachel, Connie, and Mark, for your time and for your passion for astronomy.
Thank you very much for the invitation.